Okay, so today we will continue with yesterday lecture and continuation of design example, and when we finish, after that we will talk about signal flow graph and differential architecture of switch capacitors, and then finally an example of a commercial switch capacitor filter in PSOC, programmable SOC. So I just will give a quick review of yesterday lecture. Recorded version of this lecture will be given here on Friday. So eventually what is important for you to know what are the required characteristics in Z domain for the design. If you know that, then the remaining part will be straightforward. Even you don't need to know what will be the corresponding filter in S domain. Means that really knowing what will be the corresponding filter in continuous time domain will be of no use. Therefore, practically, it's enough to know characteristic of filter in Z domain. So that's why I don't, as such, emphasize on the converting Z domain to S domain. So just if you know the characteristics, even whatever we discussed yesterday may not be required, because just you know what are the characteristics and then go straight forward. Only if you want to know what will be the continuous time counterpart and characteristics, then you need to be worried about like whether this condition omega t much less than 1 is valid or not and other things. So that's why I quickly cover this. So this was a first order filter. So it's a very general, and counterpart of that in discrete time will be this, and here we are using backward-Euler approximation. And then we learned about switch sharing. Now we can reduce number of switches. So that also we did. And then we have the characteristic of filter in S domain. Then we use, for example, one of the conversions. You can use any of them. Here we have used backward-Euler. So in the conversion also I use backward-Euler. By the way, you can also use other conversions, as we can see how you can in fact mix these two. So anyway, so this was backward-Euler. So we use the corresponding relation for backward-Euler. We get HZ. Actually, even you don't need to do that. As soon as you have this, you can do it. Today I will show you, like just you make a SFG of this filter and then quickly you can extract HZ. It's very easy. Similar to what we were doing in S domain. And then about one example, and it was just a first order filter with a given minus 3 dB frequency. So therefore, the corresponding filter, because omega t is much less than 1, corresponding characteristic of filter is easily understood by just mapping the relation between Z and S. And because this condition, magnitude of ST is much less than 1 is valid, therefore it's very easy to convert it into S domain. Anyway, in Z domain, but just by knowing these characteristics, you can get value of capacitors. You have 3 capacitors and 2 conditions, so you assume some value for one of them and then you get other 2. And in fact, here we have 2. So you consider one and then you will get the relation value for the other. From gain, because from gain condition we have these 2 equal, so that's why actually number of variables reduced to 2. So this was yesterday example, and then the second part was just to know that, okay, so when I have a condition at which omega t is not much smaller than 1, like conditions you have in a subband, what will happen? So this was the last point. Yesterday we stopped, and then just at the beginning I started writing the equations, like if I have a 0 at 100 kilohertz, which was exactly half of the sampling rate, therefore corresponding omega in discrete time will be pi. Then I explained like, okay, so if we don't have this condition, then what will be actually the relation between capital omega and the small omega? So this relation was derived, and then which is called frequency wrapping. This is actually required only when you want really to know what is happening in analog domain. So you will derive counterpart of the characteristics in the analog domain by using tangent relation. Now it is really tangent relation, okay? And then correspondingly you will get omega 0. So we stopped here. So now I will continue from this point. Okay, before continuing, just one thing. I actually expected somebody to ask yesterday, but nobody asked. If you notice in bilinear relation, I used 1 plus s upon 1 minus s. Something is missing in this relation. Yeah, 2 by t. So just I show you, it doesn't change anything. So today I will consider t so that you will see, because it's just a normalization. It doesn't change anything. Okay, so if I consider that, then actually real relation will be right, t by 2 is there. And s will be 2 by t z minus 1 upon z plus 1. So these two are there. Then we replace z by e to the power j omega. We derive the relation. So here just we have additional relation, right? By replacing z is equal to 2e to the power j omega, you will get s is equal to 2 by t e to the power j omega minus 1 e to the power j omega plus 1, which is equal to j capital omega. And therefore from here, when you do the same thing yesterday we did, you can derive capital omega is 2 by t tan omega by 2. Just this coefficient or a scaling factor of 2 by t appears. Okay, so therefore when we wrap from, suppose now you will want to know what are the characteristics in S domain. Therefore omega minus 3 dB was 0.2 pi. Okay, this is continuation of example given in lecture 9. So therefore from here capital omega minus 3 dB will be, now we have this value 2 by t multiplied by tan 0.1 pi, which is omega by 2, which now will be 2 by t multiplied by 0.325. Okay, so now just this 2 by t appears everywhere. Then if small omega is equal to 0, so capital omega will be 0, and then we have 0 at pi. So what will be the corresponding frequency in continuous time? That of course will be 2 by t tan pi by 2. Therefore this will be infinite. So therefore this means that if you have a 0 at pi, and it makes sense, right? Because essentially what it does, you have the entire frequency band as a characteristic, which is used for determining characteristic of the filter. After all, by this you are compressing the entire band in a band from 0 to pi. So that is the reason. 0 to infinity is mapped or is wrapped into a frequency band from 0 to pi. And this therefore effectively this 0 now will be mapped to infinity in the continuous time domain. Now this is interesting because if you have a 0 in s equal to infinity, this means that you don't have any explicit value. It is just enough to have denominator 1 order more than numerator. Then automatically you will get a 0 as s equal to infinity. Therefore, in S domain, your transfer function will be just the first order without any 0 in the numerator. So it will be something like this. Okay, and then P. And because this is first order, therefore minus 3 dB will be same as pole. Therefore, P easily will be in the continuous time 2 by T multiplied by 0.325. And H0 of course is gain as low frequency. So now you will get the counterpart of this filter in continuous time domain. And then here we just, the only information which helped us was more detailed and accurate relation between omega, capital omega and small omega, which is not a linear function. So this wrapping is done. So therefore now when we want to map it back, now we want to map it to the digital domain or discrete time domain. So we are careful that now we are using the realistic value, using any transformation we do. One thing is just I don't write. Yesterday we derived the characteristic of this first order filter. If you ignore, if you remove C1 so that you won't have a value at Z at non-zero Z, therefore you will have this, I make C1 equal to 0 in this filter. Okay, so I just remove C1, therefore this 0 will be removed. I have only one pole. Now if I want to keep this C1, then I will have a complete HZ. We will continue with the complete architecture. So this is same filter, C1 and C2 both are there. Therefore I will have a finite, it is resembling a finite C in S domain. But then now I want to see that if I want to convert it to, if I want to derive values, what will be the corresponding values for C1, C2, CA and CB. So now the new transfer function HZ considering both C1 and C2 will be minus CA plus C1 into Z minus C1, CB plus C2 into Z minus C2. Okay, so this is the transfer function of the first order switch gap filter considering C1 and C2 both present. Therefore, we will have one pole and one zero. However, if you notice, corresponding filter in the continuous time domain doesn't have a finite 0, but here we will have a 0, which was at Z equal to pi. And Z equal, omega equal to pi. And omega equal to pi actually is the wrapped version of S is equal to infinity. Okay. So now we have this transfer function and now we know the characteristics. We want just to derive the value of these 4 capacitors. So I know my pole, now I write in this way, right? I write SP. The reason I write SP because I want to discriminate between Z and S domain. So here also I could have written like, maybe here just I will write SP, SP. Okay. So this is in S domain. So now we have this and then now we want to see what is corresponding filter in Z domain. So SP was 2 by t. I just purposefully I keep 2 by t. I don't multiply it. So now I use bilinear transformation. Just to show you it doesn't have any effect. See, it is just like you have normalized because SP is multiplied by 2 by t and here I have t by 2 SP. Therefore, automatically it gets cancelled. That's why I didn't write t by 2. Okay, so this is ZP. Then I have one SZ equal to infinity, right? This corresponds by Z equal to minus 1. And therefore, I can now write HZ. Some constant value H, what I should call it, H1. Z plus 1, Z minus 0.51. ZP is 0.51. Yeah? Should be greater than 1. It should be inside unit circle. Oh, maybe I have. Okay. Let me check. No, actually it will be 1 plus 0.325 divided by 1 minus 0.325. Okay, then maybe reverse. Just let me check. What was the relation? Just cross check. 1 plus upon 1 minus, right? SP is 0.325, right? Because omega is tan omega by 2, small omega, capital omega. It's 2 by t tan, so it will be 2 by t by this value. We can calculate tan 0.1p. Yesterday we calculated, right? One of you calculated. This 0.325. Omega minus 3b is positive, pole is negative. Okay, got it. Okay, so therefore here actually so what will happen is this SP is actually this coefficient, okay, this location of pole, but pole is minus SP. Correct. So pole, I will write like this, pole is equal to minus SP, therefore this will be minus. Now this becomes minus, this is plus, correct. So this will be minus, this is plus, this will be around 0.7 divided by 1.3, which is around 0.5. It's not exactly 0.7, 0.6 something, so it is around 0.5. This shows you listen carefully. Okay. Then this is infinite, this is correct, right? So till this point everything is correct. So now we will have Hz. Okay, now this is to learn how this process goes. Now we will compare it with the transfer characteristic of filter or transfer function in Z domain. So just we will, okay, if I can write it here, might be better. Hz equal to minus, just, okay, I have written here. Okay, so I don't write it again. I mean, it's okay, I will divide by C1, the reason is here, or I just keep it because then just I want to explain also something. Ca plus C1 into Z minus C1, okay, just Cb plus C2 into Z minus C2. Just a small point over here. See, at the first glance, if you notice, you see 1 over here, and then over here you see C1 upon Ca plus C1. Then you may think it is not possible ever to make these two equal, right? Because this side you have 1 and this side you have C1 upon Ca plus C1. So, okay, now see how we can make these two equal. So, I write it in this form. I have factored from C1 in the numerator and Cb plus C2 in the denominator. Okay. And the reason I did this because I wanted to keep this 1 over here. And in fact I factored from minus C1. So that's why now it will be plus, and here in the numerator we will have 1 minus something. Okay, so we want to make this equal to okay, just write it H1, doesn't matter, I mean after all it's just a matter of sign. Z plus 1, Z minus 0.51. So now we will get these equations. And then for Hz, if I want, suppose for example, for simplicity I consider H at Z is equal to 1, this is 0 frequency. This means that H1 equal to minus 0.25. If you keep just Z equal to 1, it will be 2 upon 0.5, it will be around 4, therefore H1 will be 1 upon 4 multiplied by minus 1, it is minus 2.25. So this makes, just to have less number of variables. Anyway, now we will continue. Now here, so what is the location of pole? C2 upon Cb plus C2. This should be 0.51. Now, what I want is Ca plus C1 upon C1 to be minus 1, right? Then I can get Z plus 1. and of course now C1 upon CB plus C2 is equal to 0.25. So you have three equations for variables. Okay, so this is relation 1, relation 2, relation 3. So from 1 and 3 you get ratio of C2 by C1, which is 2, almost 2. Okay, I just rounded the values. So for example, now you consider some value. For example, you consider C2 because you have 4 capacitors, 3 equations. You consider, for example, assume C2 is equal to 4 picofarad. Therefore, C1 will be 2 picofarad. So now going here, so you have CA plus C1 is equal to minus C1. In other words, CA is equal to minus 2 C1, which is minus 4 picofarad. Okay. So interestingly, this is a negative capacitor. And then finally, this ratio of gain CB plus C2 is equal to pole relation 0.5. From here, because now you have value of C2 4 picofarad, therefore CB will be almost 4 picofarad as well. So now you know all values, right? So therefore now, like we have designed a first order switch cap filter with the characteristics which was given in the example. Now, how to implement a negative capacitor? What did you do in continuous time? Fully differential, exactly. So we will go with a fully differential architecture, and actually differential architecture always is better from linearity point of view, from dynamic range point of view, and even SNR. Therefore, we will go with a fully differential architecture, and then just by changing the polarity of connection, we can make a negative capacitor. Okay, so now just I draw the fully differential architecture, and the way just we choose polarity of connection and consider switch sharing. Minus plus plus minus. It is good always like you draw a schematic. When you draw a schematic, you learn it better instead of just looking at the schematic. Okay, so this was just a simple 2 capacitors in the loop. Okay, I keep them over here, C1 and C2. These 2 were there. So which one is negative? Capacitor CA. Therefore, when I want to use connection for CA, I will change polarity of input. Okay, so here will be V in plus, here will be V in minus. This is V out plus, V out minus. And then we sample it either in phi 1 or phi 2. There is a small comment here also, I will explain. Let's first draw the entire schematic. Then we should go with CA, which was playing role of resistance parallel to C1. So phi 2. There is a phi 1 here. Right. And then again here we have two switches, phi 2, phi 1. Because CA was negative, therefore here I will use Vn plus. And then again correspondingly same architecture will repeat over here. So I just show it here, phi 1, phi 2, then capacitor Ca, then again you will have phi 2 for ground connection and phi 1 for connection to input Vin minus, and only one is left which will be resistance parallel to C2. We use switch sharing, therefore here we will have direct connection of CB. In fact, switches in the left side of CB are not required, already we have two switches for CA, same will be used for CB. Only right side we will have one for ground, phi 2, and we will have one for phi 1 which will be connected to output. And similarly we will have here again phi 1, phi 2, then capacitor CB, and CB doesn't need left side, already they are there, so just we connect it to right half plate of CA. So now this is a fully differential architecture of same filter that we designed here. And then values will be, for example, these are the values. You could have used a smaller capacitor. Now one point here, of course, there is one small point regarding value of capacitor. See, when you use differential architecture, eventually your swing becomes double. Okay, if you look at the single-ended swing of V on, single-ended swing of V in plus V in minus, single-ended swing of V out plus single-ended swing V out minus. Suppose if you have some swing at each point, when you get the difference of these two, your swing will be double, right? Then means that your power, signal power will be 4 times more. Then means that differential architecture is useful to improve swing as well as signal to noise ratio. However, now what about noise? If you look, if you use same value of capacitors, then your KT by C noise will be double here because you have twice of the number of capacitors compared to single-ended version, right? And therefore, eventually means your signal to noise ratio now will be double compared to single-ended case if you keep value of capacitors unchanged. Now, if you want to achieve, we don't want to use this extra area because double number of capacitors and single-ended signal to noise ratio that you derived is enough for you, then you use half of the capacitors everywhere. Now, you will have same signal to noise ratio and your area will be less. Therefore, here you can just easily, because it is everything in switch capacitors depends on the ratio of capacitors. So therefore, you can easily scale all of them by factor 2. So this means that eventually instead of C1, which was for example 2 picofarad, you can use 1 picofarad capacitors here. Therefore, you can easily just divide them by 2. This means that eventually instead of using C2 2 picofarad, you assume it is 4 picofarad, you consider 2 picofarad for differential architecture, all values will get scaled by factor 2. Okay, so therefore here what we do is that eventually we keep SNR assuming that contribution of op-amp to the noise has not changed, therefore SNR remains almost constant. by just making capacitors. So we save area. And if we assume that area is mostly occupied by capacitors, then it will be half. But of course, op-amp also will have contribution because of compensation capacitor. Okay, so now we had one complete example. I think this is quite clear. Practically, again, if we want to expand this theory, again similar to continuous time. For example, you can have biquads. You can use cascade of biquads. Eventually, any architecture that we have in continuous time, you can convert it to switch capacitor. And then actually you are not so, you don't need to know what is the corresponding values in continuous time, just you need to know what are the corresponding values in discrete time. Therefore, it is good to know just quickly, directly, how you can get the transfer function of a given switch capacitor filter easily. So that's why it's better to use signal flow graph. That's why here, just I give you this standard architectures that when you can just easily use them, make any sort of biquad transfer function. So, yeah, that also is a good question. This was actually my question also always. See, the point is, we use this backward Euler. Actually, bilinear also, if you notice, bilinear is a summation of a backward Euler and a forward Euler. Essentially means that when you want to get this architecture, if you use backward or forward, it is economical because you need less number of capacitor instead of adding one backward. That also is okay because just you will add one delay and then you need to add. So therefore, you have one additional adder and then one delay component. So therefore, it is economical to use backward or forward, and then we prefer backward because we don't have a stability problem. But when you want to convert S to Z, then you are free to use any approximation you want, because after all of them are based on considering that you can consider your input either is constant or it is changing linearly. Therefore, I mean, that is fine. That is fine to use the conversion of frequency, but use architecture which is developed based on backward Euler. You can use architecture which corresponds to bilinear also by just adding a forward Euler and one backward Euler. That's fine. It is like that we use backward Euler architecture. We use a backward Euler plus one forward Euler for frequency transformation. So we have this is one standard architecture in switch capacitor filters. Yeah. By the way, regarding the sampling over here, at this point I need to mention, because we have used backward, then backward Euler, then you have this in phase phi 1, the entire input is transferred to output, and in similarly this feedback loop will work, and in phi 2, these two capacitors CA and CB will get discharged. Now we can do two things. We can sample V out in phi 2 because we don't have any connection here, therefore we can just sample it at phi 2. We can sample it in phi 1 also, but see what will happen. Suppose you have next stage, suppose this is a cascade of biquads, this is a biquad with order 1. Now if you connect it to the next circuit and next circuit is working in phi 1, then you will have a continuous connection of all switches in the path, which will increase series resistance of the charging capacitor. Therefore, if you want to sample it in phi 1, make sure that the next one, for example, suppose you have similar architecture as the next stage. Now what will happen? If that also works with phi 1, you will have a series connection of this, which makes it difficult to control when you have many switches in the forward path, because then series resistance of phi 1 here, one switch is here. Now going to the next stage, again one switch over here, again one switch over here. Then you will have 4 series switches in the path, right? So therefore, it's better to sample this in phi 2 and then now get the next output again in phi 1. If series resistance is not a problem, then you can sample it in phi 1, means that just transfer it to the output and next stage can take it. And one more thing you can do is that if you sample it in phi 1, the next stage should work with should flip phi 1 and phi 2, means that you use phi 2 here and phi 1 over there. So this was just 2 comments. Yeah, and now we have just different standard architectures. This is just a simple gain stage. Okay, so therefore this is your Vout Z. Here you don't have worried about sampling. You can sample this Vout either in phi 1 or phi 2, right? So it depends, or it depends on the other parts of the circuit. So this is just the gain. Therefore, okay, I call it C2. The reason is just I want to use same integrator with different inputs, and then the other part can be again same. C2 and this is forward Euler. So with double plate switching. So everywhere now we will use double plate switching. So this is another part. So this will be sampled in phi 1 easily. In phi 2 you will get the results. In phi 1 it will get sampled. And then finally we will have backward Euler, same as this. C 1 3. Okay, see. Phi 1, phi 1, phi 2, phi 2. We increase it. So here also, like directly, you can sample it at phi 2 for forward Euler. Again the same thing, like next depends on the next stage, how many switches you can have in series. So this will be now another Vout, say Vout 1, 2, Vout 3. So here again you can sample it in phi 1 or phi 2. Okay, anyway, now if you want to have a different combinations of them, see, I mean any way they can be connected. So after all, what you need to do is to see what is the corresponding flow graph with this. This is simply V in Vout Z, which is C11 by C2. And the other one was again V in, V out, C12 upon C2, Z inverse upon 1 minus Z inverse. We had this before. And for this, it is V in, V out, minus C13 upon C2. We don't have any delay, so it will be just 1 minus Z inverse. So if you notice, we have a common denominator 1 minus Z3 between these two, Z inverse. So therefore, you can always use this three. So wherever you have a feedback capacitor like this, so what I will do is that you can bring this 1 minus Z inverse into the integrator. Therefore, you can easily have this 3. And because again C2 is common, I will remove this C2. I will keep only uncommon parts. And then what is the common factor between all of them? 1 upon C2 into 1 minus Z inverse. Means that if you multiply this term by first term, you will get first function, transfer function, and so on. So what does it mean? Means that eventually you can have a signal flow graph which will have always this transfer function as the branch transfer function. Add them together and multiply it by this. So eventually, to simplify, essentially you mean that always you will have in your signal flow graph one of these three on the branches. Then you will have summing points which will have the output branch in the form of 1 upon C2 into 1 minus Z inverse. For example, if you have 3 of them, they will be, in general, they will be like this. So, for example, here just minus C11, 1 minus Z inverse, C12, Z inverse, and minus C13. Here, simply I consider V out Z is equal to V out 1 Z plus summation I from 1 to 3. I mean, the whole point is that when you see this architecture, you know that it corresponds to this transfer function. Eventually means that this branch and then one integrator. If you see the second one, which is forward ruler, you know it's a multiplication by Z inverse, which is one delay and then integrator. And third one doesn't have any delay, only C13 and then integrator. So 1 upon 1 minus Z inverse is integrator. So now it is very easy because you can even generate the corresponding flow graph directly. You get HZ, convert flow graph to forward ruler, backward ruler, or vice versa. So it is easy for analysis. This was just a small point to mention. Now, one thing I show you about practical implementations. So, in Ken Martin book, so this, as I said before, this entire topic of switch cap is based on concepts which are given in Ken Martin. Only non-idealities are based on Razavi book. Of course, chapter 10 Ken Martin book also talks about non-idealities. you can have a look. As I said, practice this and then solve the problems which are given at the end of chapter 10 in Ken Martin. I don't give you assignments, but you make sure that you have learned it. Okay. So now we go with two standard biquad, and this one of these biquads is used in Cypress PSOC. Okay. So these are two references that you will use. And I will show you, this application note. So it's essentially related to one of the application notes. So it tries to implement a complete biquad which can be programmed as a low pass filter, band pass filter, high pass filter. Can you see that? As a low pass filter, band pass filter, high pass filter and notch filter. This is a very universal, completely universal biquad transfer function, second order numerator and second order denominator. Okay, and then some definitions like roll off frequency and damping and other values. So you just read it. This is important to see. This is a switch cap version of same biquad. Okay. Now you know the configurations. Let's look at this architecture. I will draw the corresponding analog version of this continuous time. So see, here you can see, first of all, you see switch sharing, the same thing we did, right, between C2 and CP. So one capacitor is already there, the same thing we had in first order. Here you will see emulation of one resistor, right, using backward Euler. Here is that integrator, which has a constant capacitor CA. The second filter uses forward Euler, okay, and then again integrator. So here you have one RC, here you have one RC, and then you have one C here and one C here, CP and C double P. This helps to generate zeros. And then you have one capacitor CA from output to input here, and then finally one resistive feedback RC, R. I will draw the corresponding, actually there are two universal biquads that I will show you, and then Cypress is using the one which is appropriate for making high Q filters in switch capacitor domains. I will explain why it is. So first I will draw the corresponding analog version. Okay, so this is the corresponding continuous time domain of same filter. With normalized value. So this is first integrator. So these values are given according to the characteristic of transfer function. I will write transfer function. So RC at the input, integrator, again another integrator. We have a forward by capacitor K2. Then we have a RC feedback from output to input. So it's a universal biquad. Capacitor is 1 upon Q and resistor is 1 upon omega 0. And the transfer function is this. See, as you notice, putting two capacitors from input to output in the path, in the summing path. See, this is at the summers point. This here you will write KCL when you draw SFG. In fact, you can draw now SFG for continuous time also, similarly. So, K2 and K1 are in fact, depend on the value of these two capacitors which are in the direct path from input to summing point. That's why it adds 0. And of course, in contribution with this resistor. Otherwise, your one of your zeros will be at S equal to 0. Then your denominator, which is again second order, is controlled now by this RC feedback, and here C1 and C2 are 1. Of course, notice here you have 4 capacitors, but order is 2 because you have 2 loops made by capacitors. So 2 capacitors eventually are made because we want to create zeros. Now by this normalized value, exactly you see how value of components determines transfer function. Okay, so now what you can see here, now you have it in your notebook, right? So now you can compare it with switch capacitor version of the same circuit. Now look at your notebook, you will see Cp is in fact K1 by omega 0. The resistor which is made by C1 is omega 0 by K0. Resistor 1 upon omega 0 is made by C2, and so on. You can follow up. Okay, so here there is a small point. When going from V out 1, so V out 1 is here. Going from V out 1 to V out 2, instead of backward Euler, forward Euler has been used. The upper part still uses backward Euler, only this section uses forward Euler. And therefore, in the PSOC, then you do one thing. The question here is, so if you replace forward Euler with backward Euler, you derive it and then compare it with what is given in the application note for V out Z upon V in Z. Because it adds a delay, right? So we expect to get one term, additional term Z inverse. You check, you replace and then see what will be the new HZ. For example, here if you notice, inside this filter we have at least these two internal stages are connected. If you notice, we have phi 1 for discharge and phi 2 for sampling input and transferring to output in backward Euler. The next stage uses phi 1 for sampling. C2 and C3. C2 and CP. No, this is because of switch sharing. We have here left side there should be two phi 1, phi 2. We remove them because already C1 has phi 2, phi 1. So this we have removed. In fact, they have also removed phi 2, phi 1. That is correct. They are here. I explained it yesterday, right? Switch sharing. For example, look at this architecture. Okay, and look at nodes A and B. So look at nodes A and B. Okay, so these two nodes will be connected to virtual node in phase phi 1. They will be connected to AC ground in phase phi 2. And then there will be, of course, nothing will happen when phi 1 and phi 2 both are 0. Therefore, what we will do is that we will remove two of these switches, because after all, we know that these two switches follow each other when we need. And then when phi 1 and phi 2 are 0, no transaction is happening. So therefore, we just remove two of them and we share this. And because we are removing, therefore we need to connect this node to a switching node. That's why we connect B to A. Now if we connect B to A, so left plate of CB will come over here to node A. So left plate now is connected to node A. And then now you have phi 1, phi 2, these two are removed and the remaining part will remain as it is. So same thing has happened here. So left plate is connected to left side of the switching network. Okay, yeah. So I was saying that because this is sampling input at phi 2, then output is sampled at phi 1. Therefore, you don't have that problem of having so many series switches in the signal path. Okay, so this is just internally. Then now in phi 1, out 1 will get transferred and in phi 2 it will come to the output. So for example, now to analyze this, see they have written exactly in fact the straightforward version of that signal flow graph. So here for example, therefore you can just write it straightforward. So this is first for example for V out 1. So when we want to draw the signal flow graph, okay, no, actually here they have not written the way I wanted to explain for you using this signal flow graph. Here what they have written is, I mean here like for example, if you notice for backward Euler, we have 1 upon 1 minus Z inverse, and this is V in, this is V out. So, and this is the summing point. So, the way we write V out 1 versus this V in, right, this part. This is summing point, and this summing point has these components. One is V in which is coming through this backward Euler. One is this point which is eventually virtual ground, therefore it doesn't have any effect. So this part doesn't have any effect at this here. And one is from C2 path which is coming from V out 2. So if we write KCL, so it is same signal flow graph that we had. So V out 2 is one of the inputs coming by backward Euler. V in is one of the inputs coming directly by CP, and then V in again is another input coming by backward Euler. So therefore, if you look at the signal flow graph in your notebook, you just replace each one of them, two of them by V in and one of them by V out 2. And this is the integrator. Therefore, you can write V out 1 versus V out 2 and V in easily. So here actually it's not completely, I don't think it is. C1 upon CA, for example, is here. This actually should be 1 minus 1 Z inverse should be here. Yeah, no, it's not that. So you don't need, I mean, you can also look at this, but the way I explained it is easier. It's a straightforward. See, we have only these three standard architecture, and then we just put them over here. So here, if you want to extract the transfer function in Z domain, so I just draw the just input part so that you will see how it is. So it is V in. So I use the signal flow graph. This is first part. The second part, which is backward Euler, will be C1 backward Euler. So it is minus C1. And we have one more from V out 2, which is again backward Euler C2 minus C2. These three will be added. And will be given to integrator, which is 1 upon CA into 1 minus Z inverse. Now this will be V out 1. Okay, all Z. So eventually these two are same. I mean, what I mean is that now it's very easy in these cases. So now you have this, come back to this. You can get easily relation between V out 1 and V in, V out 2, V in. You have one more here, you have one more integrator, you write, you have two signal flow graphs, and from these two you can easily get V out 1 upon V in and V out 2 upon V in. So finally, C4, where is C4? Oh yes, correct, sorry. So we have one more. C4 again is direct connection. So it will be minus C4 into 1 minus Z inverse, and this is V out Z. And you draw one more signal flow graph. Okay, you continue it, you draw another one. This SFG will be for second integrator. Now you will get just two equations which will give you the relation between V out 1 upon V in and V out 2 upon V in. So it is given finally here. Okay, they have given the relation. So both outputs are available from IC. Yeah, but it doesn't change anything. No, it doesn't have any effect. C4 is this capacitor, 1 upon Q. No, it doesn't have any effect. From output to input and C1 and then C2. Phi 1 of course doesn't have, Phi 2, these two are connected. because value of V out 2 changes only we are in phase phi 2. And in phase phi 2, these two nodes are connected. And in phase phi 1, V out 2 remains constant, and anyway this node is disconnected. So it doesn't have any problem. And phi 1 is only matter of transferring to the C3. In this cascading, now you see the effects. For example, here of course your input has been from some source somewhere, but now for the second stage your input is from the previous stage. So it's very important for this op-amp to have low output impedance. And the current which is required to charge capacitor C3 should be provided by op-amp. At a given time. Therefore, slew rate of op-amp also is important. Bandwidth of op-amp also is important. And drive capability of op-amp. Okay, so then two transfer functions, equivalent values in frequency domain, continuous time domain are given here. They have used direct bilinear transformation to show it, but anyway, I mean, in general, we saw it here. Only one thing here, if you notice, in first output, when frequency S is equal to 0, output 1 is 0, therefore you don't have at S equal to 0, you have a 0, but for the second one, at S equal to 0, you have a limited. So only the difference here is that one of them doesn't have this constant term. It's here. V out 1 doesn't have this constant term K0. This K0 is not there in V out 1. V out 2 has K0. Okay. So you read this application note. It's a very interesting practical implementation of what is available in textbook. For example, you see analog version of same filter in Ken Martin book, and as well as switch cap version of same circuit, now which is actually implemented in a practical commercial IC. And then you read it completely. Then they explain about how you can program it. So, some definition like oversampling is Fs upon F0. And some examples, for example, suppose if you have a 5 kilohertz filter and your sampling frequency is 250 kilohertz, therefore your oversampling ratio is 50. This is definition they have here for oversampling. And 5 kilohertz can be, for example, it depends what is F0, if it is roll off or minus 3 dB frequency or whatever they have designed. Then suppose if you want to change the roll off of the filter, therefore, and you don't change the capacitors, then this means that your sampling frequency also should be scaled by the same value. And then they have they have a tool which is called filter calc. Filter calc actually gives you the value. So you give the characteristic of the filter you want, and then it will give you the values. And then these values have been defined, damping and roll-off frequency. And output file is in the form of Excel sheet. Values are given with examples, okay, and with plots. So you read this application note, and then of course they have a simulator associated with it. Now the question is how we can simulate switch capacitor filters. See, in old days when we had only transient analysis available. The one way was to, in fact, just recently also we were using, to sweep frequency, not in AC domain, because it's a switching circuit. So you need to apply a sine wave at a particular frequency and then simulate at a sampling frequency, get value of output, amplitude at the output, repeat it for another frequency and so on. But this will take a lot of time, right? But one way of doing it very precisely is periodic steady state analysis. This analysis is available in commercial simulators, but it is not available in open source simulators. So I want you also to look at the manuals for PSS analysis, which is given in the any simulator that you are using in the lab has it. Other than open source, for example, NGSpice doesn't have. You look at PSS analysis. There is also one document how to simulate switch capacitors using PSS. In fact, there are many documents. You can see Cadence also has, Mentor Graphics has, HSpice has. So when we want to simulate switch capacitors, then we go with PSS analysis. And one more thing is, I will be available on Monday. Again, if you have any question about switch capacitors, I think it will be good to have a quiz only on switch capacitors. I don't give you any assignment. However, I tell you, like you read chapter 10, Ken Martin, specifically sections 10.1 till 10.4, including 4. There's 4 sections, and look at the end of section problems, and then we will have a quiz, then in the class for half an hour on next Friday. And then we will also solve the problem. It is good. I mean, now it's the time we can have it. It will be before your mid-sem. And then I will also start, I hope I will be able to finish this, and then I can start talking about that introduction to data converters. That data converter won't be the topic of your, won't be included in your mid-sem. So for your mid-sem, only switch capacitors and continuous time filters will be included. So that's why I am available on Monday. You try till Monday, review this portion of switch capacitor, and then if you have any question, you come on Monday, we will discuss so that we can have a quiz on Friday. And yesterday lecture will be repeated on Friday. Okay, and then look at this application note. I don't go into the details. This is a very good example of how really practically such filters will be used and programmed.